All right. So moving on to our next topic, we're going to finish up our discussion of graphs by just looking at an interpretation of graphs. So pretty straightforward stuff, but graphs are really handy tools for understanding lots of situations in life. So let me give you an example of one. So when Louise first opened her pet store, she experimented with the number of hours per week that she kept the store open. Initially, it seemed to her that the more hours her store was open, the more profit she would realize, right? But later, it became apparent that if the store was open at times with very few customers, the operation costs for heating, cooling, lights, employee salaries, and so on were greater than her revenue. In other words, the money she was spending to keep her business open was more than the money she was making by selling pet items, right? So her profits actually decreased, right? If she remains open for too long. Like if you're open at 2 a.m., you probably don't have very many customers, right? And so it's probably a bad idea. You're probably going to start to lose some of your profits. So in order to determine the optimal number of hours to remain open, she plotted her profits as a function of open hours per week for 6 months, while varying the number of hours each week. So she did a little experiment. She changed up the number of hours that she remained open, and then she plotted those, and she got the following graph, right? So obviously, if she's open for 0 hours, right? So hours are down here. This is the number of hours that she's opened, and this is the profits that she makes. So if she's open for 0 hours, then she makes $0 in profits, of course. If she starts to open up, then things start to increase a little bit, right? Until they get to this point, and then after that, they start to decrease again, okay? Because she's staying open for so long over here that, her business is open during hours that people aren't really coming into the store, so she's not selling anything. Okay, so based on the graph, how long should Louise remain open? Well, if she wants to make as much money as possible, then she should probably stay open for around, it looks like maybe 58 or 59 hours, something like that. We'll say 58 hours. So 58 hours, right? Because this is like the maximum value of this profit curve. It says, what is her maximum profit? Well, so that looks like it's right around $2,000. I mean, $1,500 to $2,000. So this is like $500 in here. So this might be a little bit less than $2,000, maybe like $1,950 or something. So I would say it's about $1,950 or so. Okay. If Louise were content making $1,500 per week, how long should she remain open? So if she's okay with just making $1,500 per week, how many hours would she have to work? Well, as you can see, the curve kind of goes up until she reaches this 1,500. Then it continues to go up for a while, and then it starts to come back down until she reaches this other point where she's making 1,500. So she could work there are two different amounts of time that she could work if she wanted her profit to be $1,500. She could either work 40 hours a week, or she could work 70 hours a week, and her profits are going to be about the same regardless of how much she works, right? So what decision you might be able to hear my dog snoring in the background. Vader. Shh. So how long should she remain open? Well, probably if she wants to work less hours and still make $1,500, then she would want to work 40 hours a week. That's probably the decision she would go with. The only reason she might go with 70 hours is if she had a bunch of employees or something and she wanted to be able to pay them because she felt bad laying them off or something, something like that. But anyway, probably 40 hours, right? So if Louise were content making $1,500 per week, how long should she remain open? 40 hours, right? 40 hours. Okay, so this is the kind of thing that we want to be able to do when we look at graphs. A lot of it is pretty intuitive, I think, but nevertheless, we'll go through some examples to kind of bring you up to speed in case graphs are not your strong suit. Some things that are usually of interest to us when we're interpreting graphs are domain and range. because that tells us, in the case of Louise up here, it tells us, how many hours she's considering remaining open. That's the domain. And what her possible profits are, right? That's the range, okay? Intervals of increase and decrease, right? So we want to know, where the function is increasing. In the case of Louise up here, it looks like it's increasing. Her profits increase from 0 hours all the way up to about 58 hours, and then they start to decrease after that, right? So intervals of increase and decrease. Maximum and minimum values, like the maximum value here of about, I think we came up with about, it's like $2,000, but we said like $1,950, okay? Zeros. Zeros is maybe an unfamiliar term to you, but we'll talk about that when we get there. That's also a pretty important concept, and it's pretty intuitive once you know what it is, okay? So domain and range, we actually talked about that from a graphical perspective in lecture 16, so the previous lecture. We talked about intervals of increase and decrease in lecture 14, so a few lectures ago. But when we did that, we weren't talking about those intervals graphically. We were only talking about them kind of numerically. And so the definition that we had back in lecture 14 was this: a function f is increasing if f of x increases whenever x increases. And it's decreasing if f of x decreases whenever x increases. Right? So that's kind of like a numerical way to tell if a function is increasing or decreasing. If you're looking at a graph of the function, then it's even easier, right? It's easy to tell when a function is increasing or decreasing graphically. All you have to do is imagine that you're riding the graph like a roller coaster from left to right. Okay? If you're falling, then the graph is decreasing. That should say decreasing, not decreasing. Decreasing. Right? So if you're falling, then you're decreasing. If you're rising, then the graph is increasing. So again, coming back up to Louise as an example, if I imagine that I'm riding the graph like a roller coaster, here I'm increasing, right? Increasing until I get to there, and then comes the big drop, right? Then I fall. I'm decreasing. Okay? So we would say that this graph increases from t equals 0 until t equals 58, and then it decreases from t equals 58 until t equals 80, right? So let's do another example with that. So this one says, use the graph below to determine the domain and range of the function and to determine the intervals over which the function is increasing and decreasing. So I'm going to color code these. So remember, the domain, graphically speaking, the domain is the projection of the function onto the x-axis. Okay? So if I imagine taking this function and kind of pinching it onto the x-axis, what numbers get covered up? Well, this is not an arrow. Notice that's just a point. And so the function would start here, and it would go this way. And this is an arrow, and so that indicates that it's going to keep going forever on and on in that direction. You can barely see the color, but that's like a green color, right? So the domain would be everything from -4 to infinity, right? So the domain is -4 to infinity. Okay? What about the range? Well, the range is the projection of the function onto the y-axis. So if you imagine taking this function and kind of pinching it onto the y-axis, what numbers get covered up? Well, everything from here down would get covered up, right? So that's the range of the function. So the range is going to be, well, remember we have to go in order from smallest to largest. So don't say 3 to -infinity. You're going to say -infinity to 3. Okay? -infinity to 3. Okay? Intervals of increase and decrease. So we'll imagine that we're riding the function like a roller coaster from left to right. And we're rising, rising, rising. So we're increasing on this interval. And then after that, we fall, right? So we're decreasing on that interval. Now, a common mistake that students will make when they're talking about intervals of increase and decrease is that they'll give the output value. So they'll say, oh, well, I increase from y equals 0 to y equals 3. And then I decrease from y equals 3 to y equals negative infinity or something like that. But that's not quite right. Okay, we don't give the intervals of increase and decrease by the y values. We give them by the x values. So we say we increase from x equals negative 4 to 0. Right? So on that interval from x equals negative 4 to x equals 0, the function is increasing. Okay? And then we decrease from 0 to, it looks like from 0 to infinity. The function is decreasing. So we're increasing from negative 4 to 0, from x equals negative 4 to x equals 0. And then we are decreasing. And actually, you know what? I should probably use parentheses here instead of brackets. I'm not sure what your book will use. It doesn't really matter. I'm not going to take off points for something like that. But it's increasing from negative 4 to 0 and then decreasing from 0 to infinity. Okay? So that's how intervals of increase and decrease work. Here's another example. Now, this was not really an application type of problem. This was just like looking at the graph of the function. But here's how it could come up in the real world. Not that necessarily you're going to ever see something like this, I guess, in your job or whatever. But you know, this is why we talk about these kinds of things. So this one says the average temperature at any particular geographic location is determined primarily by the latitude, that should say primarily by the latitude and altitude of the location, as well as its proximity to large bodies of water, right? So if you're close to an ocean, and you'd have to be pretty close, right? Like here in the Central Valley of California, the ocean doesn't really help us moderate our temperatures. But if you're on the Central Coast, right, it's like, 65 degrees all year. Because they're right next to the ocean. Anyway, so your altitude, right, how far you are above or below sea level. Your latitude, how far you are from the equator, okay? And then proximity to large bodies of water. Anyway, the graph below depicts the mean temperature at sea level. So we're assuming the altitude is 0, right? So we're saying, well, forget all of the forget about the altitude variable. Just forget about that. We're only going to look at sea level things. Okay, so the mean temperature at sea level as a function of latitude in the northern hemisphere. So we're only focusing, we're narrowing in on latitude, right? Latitude. Okay, so over here we have the mean temperature. And we're used to seeing these numbers over there, but that's okay, right? They can be labeled over here. That's perfectly fine. So the mean temperature, negative 30 all the way up to positive 30. And then we have the latitude. So if you're between 0 and 20 degrees latitude, right, then you're like in the tropical zone. A little more than 20. I think I don't remember. It's like 22 or something. But if you're between that and, that, 62, 63-ish, then you're in the temperate zone. So this would be latitude, degrees of latitude above the equator, right? And then if you're above that 63 degrees or so, then you're in the polar regions, right? And what we see here is that in the polar region, the mean temperature is, like if you're at 80 degrees latitude from the equator, the average temperature is about negative 20 degrees Celsius. Right? 0 degrees Celsius is freezing. So this is 20 degrees below freezing, right? That's the average temperature. If you're in the temperate zone, so like 40 degrees latitude, I should have looked up what the latitude of Visalia is. But anyway, if you're at 40 degrees latitude, then the average temperature is maybe something like 7 degrees Celsius. There's 10 degrees Celsius. And here this is telling us about 1 degree Celsius every 145 kilometers traveled toward the poles. In other words, so So the slope of this, like if you treated this like a line, it's not really a line, but if you treated this portion like a line, then the slope of it would be -1, right? So you drop 1 degree Celsius for every 145 kilometers that you go above the equator or below the equator. Anyway, let's answer some questions. Part A says, is this function increasing or decreasing? Well, a second ago I said if you treated this like a straight line, the slope would be -1. And that should kind of tell you, well, it must be decreasing then, right? Another way to see that it's decreasing is, again, ride it like a roller coaster, right? You are falling the entire time. So it's a decreasing function. Okay. Part B, approximately what is the temperature for most locations between 0 and 20 degrees latitude? So between 0 and 20 degrees latitude, what is the temperature? So that would be about, oh, it's kind of hard to say, right? But if you kind of go straight over, it looks like maybe 23-ish degrees. So I'm going to say, so it says approximately what is the temperature? I'll say it's about 23 degrees Celsius. Okay. By how much does the temperature decrease as you move from a latitude of 20 degrees to 80 degrees? So as you move from a latitude of 20 degrees to 80 degrees, how much does the temperature decrease? Well, at 20 degrees latitude, at 20 degrees latitude, you're at, maybe we could say 22 degrees Celsius. Right? So at 20 degrees latitude, the temperature is 20 degrees, or I think we said like 22 degrees Celsius. At 80 degrees latitude, it looks like we're at about, -22 degrees Celsius. So to see how much the temperature has decreased, we could just subtract these numbers, right? So if we do 22 minus -22, that's really 22, plus 22, which is 44. So it decreases by about 44 degrees Celsius. So there's a 44 degrees Celsius decrease in temperature. Okay. Okay, last question about this graph. It says, if you wish to live in a region where the mean temperature is above freezing, so above 0 degrees Celsius, below what latitude must you live? So you want the mean temperature to be above freezing. So here's the freezing temperature, and you want the mean temperature to be above that, right? So at what latitude must you live? Well, let's see. I'm gonna kind of take this over to the function. So below what latitude, right? Because above this mark, if you're above this mark, then the mean temperature is going to be below freezing. If you're above this mark, then the mean temperature is going to be above freezing, right? So you need to be below that mark. You need to be below whatever that mark is. That's maybe 50, something like 55, maybe 50, between 50 and 55 degrees latitude. It's hard to be exactly precise, but if we said 50, right? 50 is like right in the middle, so 50 is maybe like right there. If we said 50, then for sure you're going to be below 0. So I'm going to say below what latitude must you live? About 50 degrees latitude. Right? If you're below 50 degrees latitude, then you're definitely going to be above freezing. The average temperature is definitely going to be above freezing. Okay, So there's that one. So that's increasing and decreasing. Next thing I want to talk about is maximum and minimum values. So to do that, let's note that where a function changes from increasing to decreasing, or vice versa, the graph has a little hill or a little bump or something, right? So here's a picture of that, right? So let's say that that you have some function, right? And it increases for a while, and then it starts to decrease, right? And it maybe decreases for a while before it starts to increase again, right? So notice that where it changes from increasing to decreasing, you get this little hill, and you get this crest, and we call that the maximum value, right? That's the maximum. Actually, to be more specific, the y-coordinate of that point is the maximum, okay? Meanwhile, if you're decreasing for a while, and then suddenly you start to increase, well, then you're going to reach a little valley, I guess we could call it, and we call that point the minimum, right? Okay, so we call the functional value, or in other words, the output value of such a bump, right, a maximum if it is the largest value in the neighborhood, and a minimum if it's the smallest value in the neighborhood. And what I mean by neighborhood is like if you take some kind of subsection of this graph, then the maximum has to be the tallest point in that subsection. The minimum has to be the smallest point in that subsection. So you can clearly see this isn't the largest point on the graph, because over here there are going to be larger values. But within, say, this neighborhood, it is the largest point, right? And same thing with this one. This isn't necessarily the smallest point on the entire graph, but within a certain neighborhood, it is the smallest point. And so we call it a minimum. Okay? Okay, so let's look at an example. This one says graph f of x equals 0.75x plus 3.5 for the domain d equals the interval from 1 to 10. Is this an increasing or decreasing function? Find the maximum and minimum values of f. Okay, so let's do some scratch work to graph this thing. So I'm just going to make a table of values like I usually do. The values I usually plug in for x are like -3, -2, -1, 0, 1, 2, 3. But notice that my domain here is just the numbers from 1 to 10. So that might be a better thing to plug in, would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And maybe I don't need to plug in that many points, right? Because I know from the format of this function, it's something times x plus something else. That makes this a linear function, which means its graph is going to be a straight line. So really, I only need 2 points, right? As long as I get 2 points that are on the line, I'm going to get a straight line that goes between them, and that's going to be the graph of the function. So, and in particular, I could choose the endpoints, right? So that's, I think, what I'm going to do. So for x, I'm going to plug in 1, and I'm going to plug in 10. And if I need to come back and fill in some details, then I'll do that. Okay. But now let's see what f of x is when x equals 1. So I'm going to have 0.75 times x, which is 1 in this case, plus 3.5. Whoops, 3.5. That's 4.25. And when I plug in 10, I'm just going to do that, and I get 11 on the money. Okay. Now, if I'm not comfortable graphing like 4.25, I could search for a better value. Like if I plug in 2 instead of plugging in 1, I wonder what I get there. I get 5. I get 5 on the money. So if I plug in 2, then I get 5 exactly. That might be that might be a nicer point to plot rather than 1 and 4.25, right? So let's do that, right? So by the way, I'm kind of like doing the Cliff Notes version of this chart because I can tell that this is the point 2,5 and this is the point 10, 11, right? So I'm going to plot 2, 5, 1, 2, 1, 2, 3, 4, 5, and then 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And of course, this thing is going to extend between 1 and 10. So I'm not going to use arrows, right? These are the endpoints. Well, that's the endpoint. And then 1, 4.25, which, would be maybe somewhere around here, is going to be actually the endpoint, right? So it's not going to be an arrow. But anyway, I should probably get a ruler so that I could draw a perfectly straight line, but that's that function there. Okay, so there's the graph of the function. Now we can answer some questions, right? Is this an increasing or decreasing function? Well, it's clearly increasing, right? If I ride this thing like a roller coaster from left to right, I'm just rising the whole time. Kind of a boring roller coaster, right? But the function is increasing. Okay? And then the next question asks us to find the maximum and minimum values of f. Well, this one, again, this is kind of a boring function. It's just a straight line. The minimum value is going to be this one, right? Or rather, the y-coordinate of that point. This is the point 1, 4.25. So I know that the minimum value is 4.25. This is the maximum value up here. Or rather, the y-coordinate is the maximum value. And that y-coordinate, this is the point 10, 11, right? So the y-coordinate is 11. So the minimum is 4.25 and the maximum is 11, right? Okay, and that's that one. Okay, so that's it for these kind of straight lines. But of course, if the graph is not a straight line, like if it's a parabola, then it's a little more difficult to tell exactly where the maximum or minimum will occur. If you just try to plot a bunch of points, you might miss it, okay? Because it might take place at like 4.2 or something that you would never guess to like plug in, right? Fortunately, there is a formula that helps us here. You may recall from your algebra days, and if you don't recall this from your algebra days, then don't worry about it because we're about to review it. But you may recall from your algebra days that the turning point of a parabola is called its vertex, right? So if you've got some kind of parabola, remember a parabola is the shape that you get when you graph a quadratic equation, and it's sort of like a V shape but with like a curvy bottom. And that point right there would be called the vertex, okay? Or you could have a parabola that opens the other way around, right? So maybe it opens upside down like that. But anyway, the turning point is still the vertex, right? Well, so you may notice that the vertex in this case is a minimum, and in this case it's a maximum, right? Or rather, the y-coordinate is, right? So you get, if the parabola opens up, then the y-coordinate of the vertex is going to be the minimum value. If the parabola opens down, then the y-coordinate of the vertex is going to be a maximum value. Well, how do we find the vertex? Well, the vertex of this quadratic equation with just generic coefficients a, b, and c, right? Ax squared plus bx plus c. The x-coordinate of that vertex is going to be x equals negative b over 2a. Now, don't let that confuse you, because that's the x-coordinate of the vertex. The maximum or minimum is the y-coordinate of the vertex. So the good news is once you find out what the x-coordinate is, you can take that and plug it back into the function, and the output value will be the maximum or the minimum. Okay? Minimum if the parabola opens up, maximum if the parabola opens down. Well, how do you know if the parabola is going to open up or down? Well, you know that by looking at this number right here. If it's a negative number, so if a is less than 0, then the parabola opens down. And you have this situation, in which case you get a maximum, right? If, on the other hand, this number right here is a positive number, then the parabola is going to open up, and your vertex is going to give you a minimum value, okay? So, with that in mind, let's look at some quadratic functions and determine if they have a maximum or a minimum, and then let's find that maximum or minimum. So in this case, I have f of x equals x squared minus 2x minus 3. The coefficient on the x squared term, so the number that's sitting out here, is a 1, right? If you just have x squared, that's the same thing as saying 1 times x squared. So this number right here is a 1, and that's a positive number, right? So a equals 1, so a is positive. So the parabola opens up. So the function has a minimum. Okay? It opens up, right? It's going this way, so it's going to have a minimum. All right. So let's find what the minimum value is. To do that, we're going to use our vertex formula, right? The x-coordinate of our vertex is negative b over 2a. All right? In this case, a is 1, b is negative 2, and c is negative 3. So negative b over 2a would be negative 2 over 2 times 1. Negative 2 is positive 2. 2 times 1 is 2. And 2 over 2 is 1. So the x-coordinate of our vertex is 1. But remember, the minimum value is the y-coordinate. So I need to figure out what the y-coordinate is. So the y-coordinate, well, that's just going to be the function value. That's going to be what I get when I plug in 1. So it's going to be 1 squared minus 2 times 1 minus 3. 1 squared is 1. Negative 2 times positive 1 is negative 2. And negative 3 is just negative 3. 1 minus 2 is negative 1. Minus 3 is negative 4. So there's the minimum value. Okay? Let's do another one. So we have g of x equals negative 2x squared plus 13x. So in this case, a is negative 2, b is 13, and c is 0, right? Because saying negative 2x squared plus 13x is the same thing as saying negative 2x squared plus 13x plus 0, right? So c is 0. Okay, well, since a is negative, so a is a negative number, so the parabola opens down. So the function has a maximum. Right? Function has a maximum. Well, let's find it, right? We're going to say the x-coordinate, the maximum is going to occur at the vertex. The x-coordinate of the vertex is negative b over 2a. That's going to be, in this case, negative 13 over 2 times negative 2. This is a little bit nastier, right? But we get negative 13 over negative 4. The negatives will cancel and just give us 13 over 4. That's not very nice, but it is what it is, right? The maximum, that's just the x-coordinate, though. The maximum is the y-coordinate. So I'm going to say y equals f of 13 over 4. And if you're scared of fractions, don't be. Just use your calculator, right? It's going to be fine. So this is going to be negative 2 times 13 over 4 squared plus 13 times 13 over 4. And I'm just going to plug that into my calculator. Okay? So we have negative 2 times 13 over 4 squared plus 13 times 13 over 4. I get 169 over 8. You could change that into a decimal. You'll have to learn how to use your calculator to do that, but it's about 21.1, or no, it's exactly equal to 21.125. Okay, so there's the maximum. Okay, so maxima, minima, they're good, important things. The last topic that I wanted to talk about are the zeros of a function. And the zeros are as follows, right? So the input values x, for which the output values f of x are 0, are called the zeros of the function. So a 0 is just a number that you plug into the function that makes the output equal to 0. So if you plug in a number and you get 0, then the number you plugged in is called a zero of the function. Now, graphically, the zeros occur whenever the graph of the function crosses the x-axis. And let's take a look at a picture to kind of convince ourselves that that should be true, right? So let's say that you have this some kind of crazy function or something that does that, right? You're crossing the x-axis here, 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 and here, right? So a bunch of times. Now, when you plug in this x value, so let's say that this is, I don't know, let's say that this is like -5 or something. When you plug in -5, when you plug in x equals -5 to this function, we'll call this function f of x. So when you plug in -5 to this function, the output value is 0, right? Because your y coordinate is 0. And same thing when you plug in whatever this number is. Maybe this is -1, right? You plug in -1, you're going to get 0, right? So we would say f of -5 equals 0, f of -1 equals 0, etc. Right? The same thing for these other 4 points. So we would say -5 is a 0, -1 is a 0. But the point I'm trying to make is that you can tell where the zeros of the function are just by looking at a graph of the function and seeing where the function crosses the x-axis. And by the way, you may remember back from your algebra days that the place where a function crosses the x-axis is called an x-intercept. So the zeros of a function can also be called x-intercepts, if you prefer. So what I want to do is show you how to use a graphing calculator, and actually what I'm going to do is show you how to use Desmos, which is an online graphing calculator. It's really, really nice. But we're going to use Desmos to approximate the zeros of these two functions. Okay? So let me take you there. So Desmos, you just go to your favorite web browser, type in www.desmos.com. Okay, and then you say graphing calculator, and it'll take you here. And then you type into this little bar the thing that you want to graph. So in this case, I wanted to graph -0.25 times x squared. Now, if I want to get x squared, then I need to find the little caret key on my keyboard. So let me show you. On my keyboard, above the number 6, I've got that little symbol there. That's the caret key. So if I hold down Shift on my keyboard and then press 6, it'll do the little caret thing. And what that's going to do in Desmos is give you a little exponent. So then I can call that -0.25 times x squared. And then I have to arrow over, right? So I have to arrow over to get out of the exponent. So I arrow over, and then I can say plus 17x plus 19. And ooh, you can't really see the function, but you can zoom out, right? If you come up here, you can just zoom out. And then you start to see where it kind of curves over. Okay, but this is interesting because it lets you know kind of where the maximum is, right? So the maximum occurs at 308. It occurs when x equals 34, but y equals 308 is the maximum value, so that's kind of cool. But if you want to know what the zeros are, you can zoom back in, I guess, and kind of click and drag to move the graph around. But if you want to know where the zeros are, you can click on those things. And so then, so we can approximate the zeros, right? So the zeros are negative 1.1 and 69.1. Okay, and that's all there is really to using Desmos. So it says approximate the zeros. We would say, oh, I've already forgot them. Negative 1.1 and 69.1. Okay, and we can do the same thing for an even crazier function. This one is a cubic function because we have an x cubed thrown into the mix. So let's graph that one. I'm going to zoom back in. Okay, so we've got 2x caret 3, right, for the 2x cubed, and then arrow over, minus x caret 2, arrow over, minus 2x plus 3. Okay, so there's that function. Ooh, notice that this one only has one zero, and it's right there. But it also has a maximum right there and a minimum right there. Okay, so those are kind of interesting things too. But the zero is the thing that we were asked for, and the zero looks like it's about negative 1.253. So the zero is x equals negative 1.253. Okay. So that's how Desmos works. Do I have any other Desmos stuff to show you? Maybe. Although I think we can probably do the next couple problems without Desmos. Oh, so I've got, 2 more examples to show you. We're almost done with the section. This one says, a rock is thrown from the edge of a cliff h naught feet high. We read that symbol h null or h0 or h naught. I just called it h naught. Anyway, a rock is thrown from the edge of a cliff h naught feet high above ground level with an initial velocity of v feet per second. The height, h of t, of the rock above ground is given by h of t equals negative 16t squared plus vt plus h naught. If v equals 48 feet per second and h naught equals 64 feet, what is the maximum height attained by the rock? How much time does it take for the rock to hit the ground? Well, let's see. So, first of all, I'm going to plug in the numbers that I was given. I know that h of t is negative 16t squared plus vt plus h naught. But even better than that, I know that v is 48. And I know that h naught is 64. So that's the actual function, negative 16t squared plus 48t plus 64. And we're asked what's the maximum height attained by the rock and how much time does it take for the rock to hit the ground. Well, there are a couple ways that we could do this. So as far as the maximum height is concerned, so for the maximum, we're going to use the vertex formula, right? We're going to say, in this case, the variable that's being used is t instead of x. So I'm going to say t equals negative b over 2a. That's going to be, b is 48, so it's going to be negative 48 over 2 times a, which is negative 16. And if I punch that into my calculator, negative 48 over 2 times negative 16. Make sure to put the denominator in parentheses, or otherwise you get the wrong result. But you should get 3 over 2. That's not the maximum, though. That's the time when the maximum is achieved. By the way, this is equal to 1.5 if you'd rather plug in 1.5. But this is the time. So it's going to reach its maximum height after 1.5 seconds. But what is the maximum height? To find the maximum height, we now have to say, well, what is the height at 1.5 seconds? It's going to be negative 16 times 1.5 squared plus 48 times 1.5 plus 64. So again, just plug that into your calculator. Negative 16 times 1.5 squared plus 48 times 1.5 plus 64. Ooh, and I come out that comes out to 100 on the money. That's kind of interesting. So 100 feet, that's the maximum height. Okay, so that was the first question that they asked. And the second question is, how much time does it take for the rock to hit the ground? Well, notice that if the rock hits the ground, then the height of the rock from the ground is 0. And so we would be looking for the values of t that make the function equal to 0. So we want to know when negative 16t squared plus 48t plus 64 equals 0. Now, if you remember how to factor, then you can factor this, right? For one thing, we can take out, I think 16 goes into all these numbers, so we can take out a negative 16, and we would get t squared minus 3t minus 4. And then you can kind of do the reverse FOIL thing, where you call this t, what would it have to be? T minus 4 and t plus 1, right? Because if you multiply this out, you're going to get back here. Negative 4t plus t is negative 3t. If this is not familiar to you at all, don't worry about it, because I'm going to show you how you can do this in Desmos. But anyway, so now you would set each of these equal to 0 and say t minus 4 equals 0, or t plus 1 equals 0, and then solve for t. So we would, in this case, add 4, and in this case, subtract 1. And you'd get t equals 4, or t equals negative 1. So how long does it take to hit the ground? Well, 1 second before you throw it, it's on the ground, or 4 seconds after you throw it. That's really the answer, is 4 seconds after you throw it. Okay? So it takes 4 seconds to hit the ground. Here's how you would approach this in Desmos. So you just put this stuff into Desmos, negative 16t squared plus 48t plus 64. Whoops. I'm going to call it x. I don't know, if you called it t, that might be all right. But negative 16x squared plus 48x plus 64. Okay, so if we want to know when it hits the ground, those will be the zeros of the function, negative 1 and 4, just like we came up with on our own. If we want to know the maximum value, it's 100, right? Just like we came up with on our own. Okay, so you can do these things in Desmos as well. Here's another one. It says, Elof is a wood carver who specializes in making whistles. Elof knows that up to a point, the more whistles he sells each month, the cheaper the price he can charge. This, in turn, is good for business. In fact, the price P is a decreasing function of the number X of whistles he sells per month. According to, and then it gives us the how they're related. According to P equals negative 0.08x plus 12. So so P is the price that he charges, right? And it's a decreasing function. You can see that it's a linear function, and the slope is negative, so it's a decreasing function. What is the maximum revenue Elof can make per month from the sale of his whistles, and how many must he make to achieve this maximum? Okay. That doesn't look right. Is revenue spelled with an E instead of an I? I don't know. For some reason that word's not looking right. But anyway, what's the maximum revenue? Well, if this is the price that he charges for selling X whistles, then the amount, this is the price that he charges for each whistle. Okay? So it's like if you charge $1 for one whistle, then for 10 whistles you're going to charge $10, right? Or maybe better yet, like let's say that you charge $2 per whistle. Then for 10 whistles you're going to charge $20, right? It's 2 times 10. So you have to take the number of whistles that you sell times the price of each whistle. So if you're selling X whistles, then it's going to be X times negative 0.08X plus 12. So the revenue, R, is going to be X times the price, negative 0.08X plus 12. So what's the maximum revenue? I swear that's not the right way to spell it. Maybe it is. But anyway, what's the maximum revenue Elof can make per month from the sale of his whistles? So the maximum. Well, so one way that we could do this would be to distribute the X. So we're going to get R of X equals negative 0.08X squared plus 12X. And then use the vertex formula. X equals negative B over 2A. So that's negative 12 over 2 times negative 0.08. That's 75. Okay. And then R of X, or R of 75, is negative 0.08 times 75 squared plus 12 times 75. And what does that come out to? Negative 0.08 times 75 squared plus 12 times 75 is 450. Okay, so the maximum revenue that he can make, revenue or revenue? I don't know. You can look it up. I think it's this way. But anyway, the max revenue is $450. All right. So what's the max revenue? It's $450. How many whistles does he have to make to achieve that maximum? Well, that's 75, right? He has to make X equals 75 whistles, right? He has to make 75 whistles. Okay, and that's that. If you wanted to see that in Desmos, you could just put it in X times negative 0.08X plus 12. Ooh, okay. So there you go. Right? He has to make 75 whistles, and if he does, he'll make $450. Right? So that's that idea. Okay, so one last thing to say. I don't have any more examples to show you, but one last thing to say, because I think you'll have a couple problems in the homework that have to do with supply and demand. So the previous example illustrates an important concept in economics about supply and demand. As the price of a product increases, demand for that product decreases, right? If the price goes up, people don't want to pay that much, and so the demand's going to go down. Meanwhile, as the price for an item increases, manufacturers will devote more resources toward producing that item because they're thinking, oh, this item's the price is going up, so we can make more money from it. So they'll make more of it, and so the supply increases. Okay. So as the price increases, as price increases, the demand decreases, but the supply increases. Okay. So if we graph the supply curve and the demand curve together, we can see the point where they intersect, right? So the supply is going to increase as the price increases. The demand is going to decrease as the price increases. But there's this point where they intersect, and we call that the equilibrium point. Okay, P naught, Q naught is the equilibrium point. P naught is called the equilibrium price, right? So that's the X value. Q naught, the Y value, is called the equilibrium quantity. It's how much is made. Okay, so you might have some examples in the homework that ask you about that. So I just wanted to briefly go over that with you. But otherwise, that's all I have to say about interpreting graphs.